So here's putting everything together. This is what our architecture roughly looks like today.
Hey guys, and welcome to a new video. In this video here, we're going to talk about Tesla's AI Day and what they showed us with the full self-driving capabilities that they're currently developing, and what different kind of approaches they're taking to solve the full self-driving problem with computer vision and AI. So we're going to talk about the full self-driving and the approach they took, and then we're going to go over the neural network architectures that they have. I'm going to explain to them. We're going to watch some of the clips from the AI Day where they explain what they're doing, what the approaches they take, and so on. But first of all, remember to join the Discord server. I'll link to it down in the description here, and you can come join the channel, chat with us about computer vision, artificial intelligence, and so on. You can now also become a member of the channel if you want to support the channel with a small monthly fee, and everything will go to create more and better quality content here on the channel. So thank you guys. So we'll just jump straight into the video here and talk about like what Tesla is doing, what different kind of approaches they're taking. So I previously made some videos about Tesla AI and how they're using neural networks to solve this computer vision problem here for full self-driving cars. And just now, what they showed us on the AI Day is just really astonishing, like how fast they're developing, like what they're doing with all the different kind of like neural network architectures. Like they're just trying out new stuff that hasn't been done before, and they're just taking AI, deep learning, and computer vision to the next level, as we're going to see throughout this video here. So what they showed us at the AI Day was just really amazing, and we're going to cover it in depth here in this video. So one of the main things with the Tesla neural networks that they're using now to actually like solve full self-driving is that they have now changed to actually like do predictions in vector space instead of image space. So often when we're talking about deep learning and computer vision tasks, we're actually like operating in image space. So we have an image that we load in, as we've talked about in the previous videos throughout this channel here as well, in both my computer vision tutorials and also my deep learning tutorials. So in those videos and in most of the applications of deep learning and computer vision, we are operating in the image space. So we're just making detections of, for example, let's say cars and different kind of objects in the image, and then we're using that information to actually like solve our problem. So this was the approach Tesla took like 2 or 3, 4 years ago, but it just found out that to be able to solve full self-driving, like that is not like we can't really just use image space because we don't have information about like the whole environment and stuff like that. So when they change from image space to vector space, it is actually like really cool, because instead of only working with 2-dimensional images, they can actually like now work in 3 dimensions or like in 4 dimensions if we take the last dimension or the 4th dimension into account with time and stuff like that. So it's just multi-dimensions that we can use in vector space instead of only operating in 2D space with the image space. So now they actually like have an environment. So to be able to have the neural networks where the inputs to them is actually like vector space, we will also need to do all the labeling. So Tesla does all the labeling in vector space, as we're going to see as well. So they actually just have a video game or an environment that the car is driving around. Then they're labeling that data. That data is actually like, so they take the images, all the images are stitched together. So they actually like have all the images from around the car, have 360 degrees camera view around the car. Then they're stitching the images together, doing some rectification down here at the bottom, as we're going to talk about. And then they actually like just have the then they project it out to 4 dimensions or like 3 dimensions. And later on we're going to talk about like the feature queue, where they take into account the kinematics, time, and space and stuff like that as well. So they have this environment that the car is driving around, and they're making predictions in vector space as well, and the car is driving from the predictions in the vector space.
So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car.
So what we just saw here was what we just talked about, and what I already went through here throughout this video as well. So how important and significant it is that Tesla is now doing like detection in vector space instead of image space. So we just see the improvement from only doing like predictions in the image space. So we have the 2 dimensions, and now they're doing the actual predictions and also the training in vector space, and also all the labeling of the data that they feed through the neural network. So you can just see like how significant it is, instead of just doing 2D image space and then projecting out the points from the camera calibration, because we need this really precise and accurate depth-wise pixel depth, so we can actually get the depth to each of the individual points that we're detecting in the image, and that just works much better when we're doing it in vector space compared to image space, because the projection, it just gets really hard to do in image space when we're not in actual like vector space, or that we're operating in an environment like in a video game, for example. So let's now talk about the full architecture that Tesla is using for their like video or like the vision neural network. So first of all, as we can see at the bottom of this figure here, or like this model, is that we can actually like see the cameras. So we have all the images that come from the main camera, the camera, like the cameras from the pillars, and also from the repeater. Then we have the raw image at the bottom, and then after we have the raw image, they're actually like doing some both camera calibration and rectification. So they actually like change, or like they actually like transform their original image into a virtual camera image. So all the images are the same. It doesn't matter what car it comes from. They can use the same model, even though the cameras is a bit different, and also camera calibrated differently, because they just change it into a virtual camera, and then they're using those images to feed through the model. So after they have rectified the image and done camera calibration and used that information, they actually like pass the image through or the RecNet. So the RecNet is just actually like just the backbone that they're feeding it through first of all, before they're doing the actual like detections of the different kind of objects. So as we talked about in one of the previous videos, is that Tesla has this HydroNet architecture where they have a common backbone that they feed all the images through, where they're using the ResNet backbone, as we've covered as well throughout this channel. So make sure to check those videos out if you want to know like more details about like what is ResNet, what is HydroNet, and so on. But then they feed it through the backbone, which is the ResNet, and then they have heads on top of the backbone, which makes this HydroNet architecture. And then each of the heads on top of the backbone is actually like what is doing the individual object detection. So we could, for example, have a head for detection of cars, pedestrians, and so on. And then at the end here, we can actually see that they use this FPN here, which is a bidirectional, and then we have this feature pyramid network. So it's really good to do easy and fast like fast detection of these different kind of like, or fusing of these different kind of like multi-scale features, as we can see what is the output here from the network. So we have the raw image, we pass it through these three different kind of steps here, and then we end up with these multi-scale features. So these are just the features that we have fused together from the camera. So all the information that we get from the camera, we would like to like fuse these features together. And then we can see here at the top, we merge them together again, and we have this multi-camera fusion and BEV transform. So we have these multicam features. Now we can take the kinematic from the car and also the other different kind of cars driving around in the environment. So we have all these information from the sensors and also from other different kind of neural networks. And then we fuse all of them together again into a feature queue, which we're going to talk about as well. So inside of the feature queue, they both have a time-based queue and also space-based queue they use for different kind of things. So the time-based queue is that they just like over time, they just push new information to that queue. And then over time, when the queue gets pulled up, they will pull out the information again over time. So maybe the car can remember like what happened the last minute or 2 minutes before this time point that we're at now. And then also have a space-based queue where they just like remember stuff that happened before. So say that there was a road sign like 50 meters behind us, it will need to use that information to do an actual like, action where it is now. So that's why they're using these different kind of like feature queues to do different kind of stuff. And then we have this video module built on top of it, again with the multicam video features. And then we have the head here, and then for example the output of the head here for the HydroNet architecture could be the velocity of the detected cars. It can also be just like the bounding box of the cars, the actual detection of the cars, pedestrians, road signs, traffic lights, and so on. So this is the way that Tesla is structured the architecture of the neural network. So they have all these different kind of things with the RecNet, their backbone, that heads for each of the individual tasks that they're doing, and they can fuse all the information together, pass them through the same neural network, and they just like have these different kind of like queues and fusion of the different kind of like multicam features that they're detecting.
If you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space, but we are still operating at every single instant in time completely independently.
So here we saw how significant it is that they're now using the multicam instead of single cam. So instead of just taking like predictions from the individual cameras, they have now stitched all the cameras together and they're doing predictions with all the cameras together. So they actually like have just a surround camera and it actually looks like just one camera. So when they're making predictions of, for example, a truck that we saw here in the video, now it actually detects the same truck throughout the surround videos instead of in 3 different kind of video, like in the individual cameras. It will detect like one truck in each of the cameras, and then they will have to fuse them together later on. So we can just see the improvement in the accuracy and also in the confidence of the predictions of all the cars here that we saw in the clip. So the detections with the multicam was much more stable compared to the single camera, which is really, really important when we're talking about like full self-driving cars and just having this car driving around in the environment. And it also improves again the vector space that they're operating in instead of image space. So it is just such a significant and also really, really hard approach that they're taking with doing it in vector space instead of just in image space, which like almost all other applications are in. So now we're going to talk about another approach that Tesla is taking right now, is that they're using spatial recurrent neural networks together with the video module, as we went over in the full architecture at the beginning of the video here. So to use it both for the space-based queue and also for a time-based queue, so the car actually like has a memory of what is going on in the environment. I'm not going to cover like what recurrent neural network is, but it's just like, so we build we build memory into our neural networks. I have videos about it on the channel here about RNN, so go check that out if you want to know more about what recurrent neural networks are. But in this video here, we're just going to see how Tesla uses it and some of the results that they get by using this recurrent neural network.
Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road. Like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here. And basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in the space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before.
So what we just saw here was the spatial RNNs that they're using to actually so they can actually create these maps here. We saw some of the outputs for some of the different kind of layers in the actual recurrent neural network. So we can see all these different kind of things that can be put together to this 8D map that we saw as well. So the car can actually drive around, and the more it drives around in the environment, the more they will actually know about the different kind of roads, and the more cars they have in the fleet, the more data they get, and the more confident the neural networks get, because it remembers things when it's driving around in the environment, and it actually caches the information.
The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are 2 cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthroughs through what's happening, when both of them are in view, the predictions are roughly equivalent, and you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account.
So we also saw this improved robustness here to temporary occlusion, where we actually have this video neural network here instead of the single frame, and also because we're doing here in vector space instead of image space. But the most important thing here with the video compared to the single frame, and by using the recurrent neural network, so we actually can remember what has been going on beforehand. So we have this video here where we can see that we have more stable predictions when a car is driving in front of the car. So it actually loses track of the cars behind that car that's driving in front of us. But we can see from the video results that it actually remembers that those cars were behind the car that just drove in front of us. Where in the single frames, it will try to do predictions on those cars behind the other car, but we can see the uncertainty and those cars are just flickering around compared to the video predictions, which is just way more confidence. And when we add all these things here up together, both with the video, the vector space, the sequential 360 degrees around cameras, so the multi-cameras that I have, and they're working with video in vector space, it just gives so much more robustness and accuracy and the confidence in the system. And also just the way that they're solving full self-driving, we need really high accuracy and also robustness to actually be able to solve full self-driving. So the more they can get confidence into the system and and they can prove on just the better. And this is just really cool artificial intelligence. And even as Andrej Kampadis said, that he hasn't seen anything like this before here with the HD maps created with these spatial recurrent neural networks.
We also saw significant improvements in our ability to estimate depth and, of course, especially velocity. So here I'm showing a clip from our Remove the Radar push, where we are seeing the radar depth and velocity in green. And we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance. And in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network. So we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us.
So over here to the right, we can actually see all of the different kind of things that goes through Tesla's neural network while the car is driving around, together with the spatial recurrent neural network that we just saw in the videos, and how it actually construct this HD map here when the car is driving around in the environment, and got the memory about what is going on. So at the bottom pictures here, we can actually see the depth information. So the brighter the pixels that are, the closer objects or the pixels are to actually car, and the further it gets away, the darker the pixels get. So we have this depth net here created while driving around. And then the middle row here, we can see the actual object detection. So we can see the cars is detected at blue colors. We have some different kind of road signs detected as well, and also the drivable road that the cars can drive on. And then at the top here, at the top row, we can actually see the edges where the car can drive. So it just detects all the edges around the road, so we can construct this HD map here we can see at the top. So that's it for this video here, guys. We have been talking about the full self-driving, the neural network architecture that Tesla is using, and some of the new approaches with their predictions, and also the training in vector space instead of image space. And we also talked about the memory in the car with the space-based queue and also the time-based queue, and how they're using spatial recurrent neural networks to actually get more confidence and knowledge and also memory into the car when driving around in the environment. So I'm also going to do videos where we're talking about how Tesla is actually doing planning and control of the car. So here in Tesla's with the neural networks and full self-driving that we talked about in this video, is just how they actually use perception for the environment. And now and later on, we're going to talk about how they actually plan to go at the routes with the cars. So how they act combining navigation with this AI system, how they're planning to go around in around a corner or in a roundabout and stuff like that. So we're going to cover that in another video, and we're also going to cover Dojo the artificial or like the neural network training computer that is just really important to get this full self-driving to work, and also just to scale it to a really large solution. I'm going to cover those in another video, so make sure to hit the subscribe button and also the bell notification under the video, so we'll get a notification when I upload a new video talking about these different kind of things. Alongside, I'm doing computer vision tutorials, deep learning tutorials, where we're talking about some of these different kind of things here. But what Tesla introduced at the AI Day is just on the next level, and we haven't seen anything before like this. So it's just really amazing. I'm really excited for it, and we're going to cover more about it. We're going to go more into the details and the theory behind it. So thank you guys for watching this video here, and I'll see you in the next one. Bye for now.